Hello everyone and welcome to your prep screencast for chapter 21, which is on the immune system. So in class, we're going to do a little bit something different. Instead, we're going to make this huge concept map instead of going through PowerPoint slides. I do have the PowerPoint up on Blackboard if you like learning in that fashion, so it's available to you. But like I said, we're going to try a little bit something different since we don't really need a ton of diagrams and illustrations and figures and tables for this lecture. So what I want to do is kind of organize the material for you. So first thing we need to know, and this might be a little bit of review from microbiology, or I hope at least a little bit is review, but our immune system is broken up into two major immune systems, and that's innate immunity and acquired or adaptive immunity. So innate immunity, the reason why it's called innate is it's because it's something we are born with. Something we're born with. And this immunity is non-specific. You may have even heard this called non-specific immunity. And because it's non-specific immunity, that means your body just has a couple strategies. I'm just going to abbreviate their strategies that it uses to combat any type of pathogen it comes into contact with. It's not a specific thing where we need a specific antigen that we have to have a specific receptor combined with. It's whatever it is, we're going to react to it exactly the same, okay? There's no celebrities here in the innate immunity, okay? Nobody gets special treatment. And the other thing I want to mention is that this reaction is always very fast, okay? It's the first barriers, it's the first line of defense, and we'll put and here, second line of defense within our immune system. So we'll talk more about this in a minute. Let's just touch a little bit on acquired and adaptive immunity first. So this is something that we gain as we age, whereas innate we were born with. And this, you might have guessed, is now going to be specific. With this immunity, we're going to talk about this. You come into contact with a pathogen, look at its antigen there. You have to find a specific receptor or antibody that is made for that antigen, and then we have a reaction that's going to occur. So it's very specific. You kind of tailor your fight within your immune system to the specific pathogen, okay? And what else do we need to mention? That this is a very slow process because our body is filled with cells that are going through within our lymphatic system, within our blood, and searching for these pathogens, these antigens. And that takes time. And then we have to take the antigen and process it and set it up and have another cell come and recognize that. So as I'm going on and on, you're seeing this is a longer process. And we'll talk about all the specifics to that in class. So last thing we need to know is that this is our third line of defense within our immunity. All right, now that we have our summary written for each of these, I just want to touch a little bit about what these first and second and third line of defenses are and what they involve. So first line of defense, I want you to know that this consists of external membranes. What does this mean? It means that we use our skin and our mucous membranes. So our membranes that line our digestive tract, respiratory tract, urinary tract, and reproductive tracts. That's all made up with these mucous membranes that somehow have a exposure to our external environment. So we're going to talk about more specifics about how these serve as barriers to our body to work within our immune system in class. I don't want to get into specifics here. Now our second line of defense, this is more of like a cellular type of immunity. So I'm going to draw a bubble out here, and let's see, how should we do this? Well, first, let's talk about some cells and molecules. Okay, cells and molecules, sure. Okay, so we have antimicrobial, let me make sure I spell this right, proteins. These antimicrobial proteins, what I'm talking about here are things called complement proteins and interferons, which I'm hoping you guys touched on a little bit in microbiology, but we'll talk more about them in class in case you didn't anyway. So complement proteins and interferons. Great. Other cells are going to be our phagocytes. So we're going to talk about phagocytosis again. And some examples of our phagocytes, they were like our neutrophils, our macrophages, also our eosinophils. They can also serve as phagocytes sometimes. Oh my gosh, my pen is not working well today. So eosinophils as well. Okay, so we got those guys. We also have our NK cells. And these are like our police guys. I'm going to put little handcuffs here, but my pen isn't being too specific here. They police our body, specifically in our lymphatic tissues and our blood, to search for those pathogens. So more on NK cells in a moment. Other things that we're going to have are things, actually I'm going to draw out another branch here, a process known as inflammation. This is going to be major within our system. And I'm going to touch on inflammation on another slide, so we won't write anything more specific here. Now let's talk about acquired immunity. So we said this is made up of the third line of defense, and what I want to do is just say that it's consisting of our B cells and T cells. And these create another set of immunity. So our B cells are known as our humoral, or they work within our humoral immunity. Sorry guys, I don't know why when I'm writing here, it looks like something written in the Stone Age. But anyway, our T cells are going to be our cellular, or let's say cell-mediated. Running out of space here. Cell-mediated immunity. Okay. So T cells, cell-mediated immunity, B cells, humoral immunity. We're going to get into more specifics on the next slide. The last thing I want to do is say that our innate immunity and acquired immunity communicate. They communicate using the same or very similar cells and chemicals. So you are going to see that there is some overlap here between innate and adaptive immunity, but as far as the functioning, that's going to be a little bit different. So let's jump into it on our next slide here. We're going to talk about innate immunity first. I am just going to try and re-plug my pen here and hope it works a little bit better now. Where are you, pen? There we go. Okay, so with our innate immunity, we said this was our first and second line of defense. Great. Let's talk, let's see, where should we go from here? Let's talk about our skin first. Our skin has an acidic mantle. Wait a minute, that doesn't look right. Acidic mantle. Do you guys remember this from our integumentary system? What that means is our skin is acidic, and that acidity, most of it comes from the oil on our skin from our sebaceous glands, that is going to inhibit growth of bacteria. The other thing we're going to have from our sweat glands now is going to be a chemical known as dermacidin. And this is specifically from our ecerinal sweat glands, if you remember that. And this molecule is going to be toxic to bacteria as well. So right here, we've got a great physical barrier now. As soon as that bacteria touches our skin, these two things are really going to help us kill them, combat them. Bye-bye bacteria. The other thing we're going to have are enzymes. And some of these are just going to be surrounding our skin. But really, well, actually, let's make this a separate thing. Sorry about that. Let's talk about it as far as our mucus membranes, because really we have much more enzymes within our membranes than we do our skin. So our enzymes, we have our lysozymes. Do you guys remember where lysozyme is found? Lysozymes are found in tears and also in our saliva. And so this is going to combat bacteria in that way, where it'll basically kill off that bacteria entering our eye or in our mouth. We also have some enzymes within our respiratory mucosa. So I'm just going to put RM for respiratory mucosa. And we also have enzymes within our stomach that'll kill bacteria in there as well. And then just adding to our respiratory mucosa, we have cilia as well. So I'm going to put this in parentheses. So cilia assists with getting bacteria out of our respiratory system by moving debris out, either out through our mouth, or it's going to kind of filter it up and back to go into our esophagus to move through our digestive system. All right, let's see. Do we have anything else to add about our mucous membranes? Last thing, let's just also mention is mucin. Mucin, did I spell that right? Yes, I did. Okay. And mucin is going to be a sticky type of mucus that will trap our pathogen or microorganisms. Whenever I write MO in capitals, that's referring to a microorganism. And remember, a pathogen is any microorganism that can cause disease within the body. Okay, second line of defense. We already talked about antimicrobial proteins, so I'm not going to talk about more. I'm not going to talk more on that. Phagocytes, we're going to talk about phagocytosis in another slide. So the other thing I want to talk about, which we didn't write in the previous slide, is a fever. A fever can occur, and this is different heat than the type of heat we're going to find with an inflammation. This is going to assist us in inhibiting the spread of let's say, a bacteria that has entered our body. So what this fever is doing is it's raising our body temperature. And fever is going to assist some of our white blood cells in functioning better. Some of those cells just work better in the heat. And maybe that's why some people leave Chicago and go to Florida, because they can't take the cold here. They function better in the heat. They're happier. And so our bacteria too, some of them can't excel well in heat. There are some people that just overheat and sweat to death in heat and can't handle it. That's why they live in Chicago. My father-in-law being one of them. So he's like the bacteria guy. He wants to stay in the cold and function well. Whereas other people, me included, would want to move to a warmer area so they can function better there and be happier, okay? Not that I'm not happy, but anyway. So that's what a fever is doing. Now, we talked about inflammation. We're going to talk about that on another slide. Let's just add it here, inflammation. And then as far as our cells that I mentioned in the previous slide, we'll talk about all those in specific in class. So like I mentioned, let's talk about inflammation, which is a part of our second line of defense. So what are our cells involved in inflammation? Well, we have macrophages, we've got mast cells, definitely some white blood cells, and what am I missing? We also have some inflammatory chemicals, which aren't really cells, but they're secreted by cells, of course. So we're just going to group that in there as well. Now, our macrophages. Actually, before we talk about these cells, let's talk about our 4 major cardinal signs, and then we'll talk about our cells. So you probably already know our 4 major cardinal cells are going to be swelling, pain, redness, and heat. And I'm going to put this little guy as a dotted line here because some people include a 5th cardinal sign, and that is going to be inability. Actually, let's do impaired functioning. Okay, great. We've got our major cardinal signs. So how does all this happen? Well, I have a wonderful slide here for you. Okay, so the way we get swelling and pain, when we get some kind of disruption of our body, let's say it's a dirty nail has entered our skin, okay? There's bacteria on the end of that nail. So we start to get some cells around this area signaling to us, hey, there's some bacteria in here, I need some more help. And so we get these inflammatory chemicals being sent into our blood, okay? And that's going to tell our body to send in more white blood cells, more cells in general to help with our immune system, our immune attack against this. So our white blood cells all start filtering into this area, okay? So let me get my pen again. So our white blood cells are coming in and creating swelling because we're getting more blood flow to this area. And with more blood flow, we get more white blood cells that are going to come. For example, our neutrophils here and also our macrophages, which macrophages, if you remember, this can be found in our tissue. But when it's in our blood, what is it? It's a monocyte. A monocyte, remember, is a type of white blood cell. I'm going to put blood here because we find monocytes in our blood. And then once it moves into the tissue, it becomes a macrophage. And macrophages, along with neutrophils, like we mentioned earlier, are going to be phagocytes. So they come and gobble up this bacteria and leave behind some debris. Now, because we get swelling occurring from all this blood flow and the greater amount of white blood cells in this area, that's going to put pressure on our free nerve endings in here. They don't have any pictured in here, but I'm going to add one in here. So when we get more cells here, it puts pressure on these free nerve endings, and that's going to result in pain. Now, because we have more blood flow coming into this area, and this is all happening through vasodilation. So I'm going to put these two are caused by vasodilation. Do you guys remember what vasodilation is? It's our capillaries, well, all blood vessels opening up their diameter. So if this is our normal diameter of our blood vessel, it's growing and becoming larger. Okay, so we get more blood flow in this area. again, vasodilation is also going to help us along with the swelling. And when we get more blood flow into an area, it's going to become more red. Remember, we have that hemoglobin. That's a pigment. Well, the heme part is. It's a red pigment that causes our blood to look red. Where was I going with that? To look red, and that's what's leading to the redness, because we're getting more blood flow to the surface of the skin, and that's why we get this redness. And because of this blood flow coming closer to the surface of the skin, we also feel more heat production because of that. So one last thing I want to mention about inflammation is that the way these white blood cells are moving in to this area is that we're going to change our capillary wall a little bit. We are going to make it more permeable. Where should we write this? Let's write it up here. Permeable. Permeable. Great. Increased permeability of capillary. Well, that doesn't make sense because I wrote permeable. Permeable, increased permeability, let's write, oh my gosh, my brain is not functioning today, of capillary. Okay, so that is going to add to the swelling, adds to the pain, which eventually is going to help us with the redness and heat too, because we get more blood flow in this area. So it's all really a cascade effect. So the increased permeability of our capillary, what that does is it allows these white blood cells, so this one is a neutrophil, moving through the blood, it allows them to squeeze through the endothelial tissue. Remember, endothelial tissue is just simple squamous epithelium. And so the cell squeezing through is called diapedesis. Diapedesis. They squeeze themselves and move into the infected area. Okay, that's the last thing we're going to mention on inflammation. Now let's talk about phagocytosis. So I was going to talk a lot more about phagocytosis, but this lecture is taking longer than I thought. So with phagocytosis, you guys should know this as cell eating. Okay, and remember, there are three main cells that help us do this, or are men. You can't live without men. Neutrophils, eosinophils, and our macrophages. Okay, all of them are phagocytes. And the way they're going to start with phagocytosis is that they have to recognize our pathogens' carbohydrates on their cell surface. So here's my fun little carbohydrate, guys. This is like a bacteria, okay? So our macrophage, let's just say it's this guy here, we'll put an M here, is going to be moving through our tissue and it runs into a bacteria, and then it recognizes the carbohydrates on its cell surface. Sometimes bacteria will have a capsule surrounding it, so it hides these carbs all around it. And what our adaptive immunity is going to be responsible for doing is, we're overlapping here a little bit, is our B cells will create antibodies. Before that we have plasma cells, but we're going to get into that later. Antibodies that will go and coat this bacterium, and this is called make sure I spell this right, opsonization. Get a little delayed with my pen. Opsonization. So it coats this, and then the macrophage is like, oh, okay, the antibodies are signaling to me that this is a pathogen and I need to come and phagocytize this guy. So it does that. Great. That is phagocytosis. We're going to talk about the steps in class. These are the steps, but like I said, we'll talk about it or review it in class. Okay, now let's talk about adaptive immunity. Now with adaptive immunity, we said it's broken up into two different parts. We have our humoral, which remember was going to consist of our B cells, and cell-mediated, which consists of our T cells. Now, what do we need to know about our B and T cells? Well, if you remember from our cardiovascular lecture, our B cells and T cells are born in bone marrow. And then they have to mature. Where do they go to mature? Our T cells are going to mature in the thymus, and our B cells are going to mature right in the bone marrow. Oops, mature. Great. Okay. Now, what do these cells look like? Well, if you remember from our blood lecture, our lymphocytes have this huge nucleus. It takes up the entire cell almost. We have like a little lip of cytoplasm left here. So that's our B cell. Here's our T cell. Why am I drawing the same exact thing? Why is this important? Because I'm going to draw out what our receptors on these cells are going to look like. Now, our B cell has something called a BCR, a B cell receptor. And basically it just looks like an antibody attached to it. Remember, antibodies are Y-shaped, whereas our T cell, it just is what a regular receptor looks like. It just has this funky shape to it. And each of these receptors are for a specific antigen. Specific. You know how they say like everyone has one soulmate? Some people don't believe that. But anyway, it's like each of these lymphocytes has that soulmate that they're searching within their entire lives for. Sometimes they think they find their soulmate, but they're wrong. Anyway, we'll talk more about that later. That's going to be involved with, I'm going to put this up here, positive and negative selection. And positive and negative selection is going to give us immunocompetent B and T cells and self-tolerant B and T cells. What does that mean? Our immunocompetent cells, that means that they are going to bind to pathogens that are bad and attack them. Whereas self-tolerant means if they bind to our body, well, if they try to bind to our body cells, they're going to recognize, hey, I don't need to bind to my body cell because I'm not an enemy with myself. I'm an enemy to the pathogens. So that's what those two terms mean. We'll talk more about them in class. And I know I keep saying that. I got to stop. Okay. Now what's going to happen next? I didn't mean to put that dash there. Our cells, our B and T cells that have specific receptors, let's say they run into that specific pathogen, okay? And then they're going to find an antigen to bind to. Okay, so there's our antigen. They ran into the pathogen which has the antigen on it, which I forgot to review what an antigen is. I know I mentioned it in class. But let's say we have a bacterium. An antigen is going to be that marker that identifies it. It's that license, that ID that tells all cells, hey, I'm a whatever bacteria cell. So anyway, let's say this B cell finds it. This is now called a naive B cell. Okay, and this B cell has to become activated. Okay, and the way it does this is it's going to endocytose this antigen. Okay, so it comes in here through a vesicle. I shouldn't have filled that in too much. Through a vesicle, and it has a molecule in here called an MHC molecule. MHC molecule. MHC molecule. There's two different types. Actually, I'm going to move ahead here. Let's talk about MHC molecules first. Wait a minute. Oh no, it deleted everything. Okay, anyway, we're going to talk about MHC molecules and then we'll talk more about our B and T cells. All right, MHC1 molecules. By the way, these MHC molecules are all proteins. So whether it's one or two, it's protein. And this can be found on all body cells, except red blood cells. That's great because that means that we can donate blood without rejecting somebody else's blood, as long as you match the right types. Remember our ABO thing? And we also have that positive and negative thing with the Rh factor. So you can have our A antigens on your cell, your red blood cell, that makes you a type A. Anyway, I'm not going to repeat this whole thing. But our other body cells, let's say our kidney cells, okay, they have specific MHC1 molecules. And so we have to match that if we're going to donate a kidney. They have to match or else the body's going to reject it and the transplant is not going to work. Now, what about our MHC2 molecules? These are all cells that, well, they're on all cells that are APCs. Do you guys remember what APCs are? They're my gift givers, antigen presenting cells. And the two most common ones that we're going to talk about, they are going to be your B cells and dendritic cells. Your macrophages can also serve as APCs, but we're not going to use them too often. So anyway, these are required to activate those B and T cells. So that's what I want to talk about here. So let me redraw this. I'm going to pause and redraw this so we don't waste time. Oh, good. I was hoping it didn't get rid of it. Okay, so here's my B cell. There's my BCR, my B cell receptor, and it's bound to an antigen. I forgot to write naive here. This is a naive B cell. What it does is it endocytoses this, and then it has a molecule in here. MHC molecule. Which one? One or two? MHC1 molecule. Okay, so what it's doing is it takes in this antigen, okay, and it's going to process it, and it sends it first to our ER. Remember, the ER helps create proteins, right? And then it's going to take this and put it together with this MHC molecule and the debris that is this antigen and move it over to our Golgi apparatus. That Golgi apparatus is then going to exocytose this, and what it does is it puts it up on its cell surface. So now our B cell's like, hey guys, look what I got. I've got this great antigen here. Let's find my next guy, which is going to kind of combine with my next slide. Let's find my helper guy, helper T cell. And this helper T cell has that TCR, that T cell receptor that is specific, like a puzzle piece. It's soulmate, specific to this antigen. When it binds, when it binds together, it will become activated. All right, trigger that immune response. Let's kill these bad guys, right? Okay, so now let's talk about our T cells. Well, actually, we got to go back to the B cells. And there goes my drawing, it disappeared again. I just want to right after it becomes activated, what it's going to do is clonal expansion. It's going to clone itself and create all these plasma cells. Remember, this is the thing I want you to know, like the back of your hand. And that creates antibodies that are all specific toward that antigen. Okay, so we're going to talk more about the functions of antibodies in class, but I want you to know that B cells divide into plasma cells, which then will create antibodies. Okay, next let's talk about our T cells, and hopefully whatever I draw doesn't disappear here. So our T cells, okay, what they are is first naive T cell, okay? And remember, this naive T cell, draw this real quick, has to come into contact with, well, it came into contact with that B cell, but what was that B cell serving as? An antigen. Whoops, why did I draw the antigen here? The antigen is back here. Okay, and the T cell comes and combines with this antigen. And that B cell is an antigen presenting cell. So this cell is any antigen presenting cell that combines with the naive T cell. And what do you think happens when they bind? That's right, it becomes an activated T cell. But because this is a T cell, we're not going to go through clonal expansion and create plasma cells and then antibodies. That's B cells' job. Our T cells are going to go through another type of expansion and become either killer T cells, which I think by the name you can figure it out. And by the way, also a cytotoxic T cell, that's the same thing as a killer T cell. But their job is to go and find those MHC1 molecule on any of our body cells that has that specific antigen. Okay, they're searching for it. As soon as they find it, they are going to cause apoptosis to that cell. Cell suicide. Okay. The other thing it can become is more helper T cells. And these are going to help to activate those naive B cells so that these can go and become plasma cells and secrete what? Antibodies. Okay. And the other thing that they can differentiate into are memory T cells, which I forgot to mention in our B cell slide. But once the B cells become activated, they become plasma cells, but then they can also become memory B cells. So these memory T cells, what they're responsible for doing is remembering, my pen is like being weird again, remembering the what? Remembering the antigen. Okay, they're remembering the antigen so that when we come into contact with that antigen again, okay, let's say we go through the full infection, whatever, we kill off that pathogen with the antigen, and we're healthy again. Let's say we get reinfected with that pathogen, and now our body can recognize that antigen and move a lot faster. Remember we said that adaptive immunity is slow, and that's because we got to take our time finding that antigen, triggering the whole immune response. But if we already know what we're dealing with, we know who you are. We can act a lot faster. And so it's great to build up this immunological memory. That's why as adults, it's less likely for us to get sick, and kids, it seems like they're sick all the time, right? Because they're building their immune system. Also with our memory B and T cells, that's going to help us build or take advantage of that to create vaccines. So we're going to talk about vaccines in class. So anyway, I'm going to end this screencast because we're close to 40 minutes. This will become more clear in class, I promise. Okay, bye.